today, usual way, write to me over chat, and Anand, you can take over.
Good morning, everyone. So I will start from where we left on Wednesday. Basically, I introduced you to basic requirement of the structure of a star. To go through very rapidly, we find some amount of energy per unit time released by the star from the outer surface. And we computed if you want to generate that much amount of energy per unit time efficiently and keep it going for long periods of time, we will do it through nuclear reactions. Then given the condition that the same star should sustain nuclear reaction at some place and also appear to have a temperature of few thousand Kelvin in the outer atmosphere, we said that one best way of doing is what is known as hydrostatic equilibrium. Hydrostatic equilibrium at each location, right? We said you go to any radius, we will find out the outward pressure will be compensated by the force acting on that fluid, gravitational force acting on the fluid inwards. Okay, so that is the thing we have set up, and now the question is okay, you generate huge amount of energy in the center, and how you transport them to the outer surface. And I gave an analogy which is in the given here in this cartoon, and I hope you still remember. So even without seeing the source, if you know the rate at which some energy is released, you can predict what should be the rate at which the energy should be created at some point in the center, right? And we also said that just because you see water coming from this pot, in the end, you won't say that water is created here. Okay, so this is the kind of analogy you have to remember. So let me go through now what is the requirement for transport. So I will redo this part because I did it in the end. So basic requirement is the energy per unit time generated in the center of stars should be equal to the observed luminosity, and there is no accumulation of energy anywhere while transporting energy from center to the outer surface. This is what we said we have to do. Okay, now let's start possibilities. Of course, whenever you have energy transport, we talk about conduction, convection, and radiation. These are the three modes by which typically in a physical situation energy can be transported. In case of star, two things are more important. One is transport by radiation, another is transport by convection. I explained to you last time about the radiation, but I can go through it again. The requirement is that you create a photon or some nuclear reaction goes, for example, some amount of energy is released in the form of gamma rays or whatever you can, blast wave or whatever you can think of. This energy has to sort of radiate away, it has to come out. If you think of one photon being created, and if it just leaves the sun, then it is not going to interact with anywhere. So a point somewhere here will not gain any energy just because something is going on here. So the way you have to do is that the photon should, if you think of radiatively transporting, photon should be tightly coupled to the matter. So matter will absorb photon and emit photon, absorb photon, emit photon, or scatter photons, so that there is a continuous exchange of energy and momentum between photon and the particle. This is what we call as thermalization. If it is tight, if the scattering is large number of scatterings are taking place or large number of absorptions are taking place, in a technical term, if the gas is optically thick to radiation, you will find that the gas will be in thermal equilibrium with the radiation field, and the radiation can simply move like this. So at different locations, you will have different sets of equilibria depending upon what kind of gas you have, whether you have a neutral gas, ionized gas, plasma, or whatever it is. So this in principle, radiative transport is not a single parameter problem. At each location, one has to ask this question: what kind of gas we have, or what kind of particles we have, and what kind of interaction is allowed at that particular temperature and density. But in general, we will be considering all possible interactions, which includes scattering, right? And free transition. I see yesterday it was done in great detail by Dipankar. because he derived all the at least he showed all the equations which are relevant for these processes. Scattering, free reaction, both may be same, right? Bound free reaction or free bound reaction, that means either you ionize the gas because the electron is removed from an atom, or you create an atom by electron joining to a ion, right? So this is this kind of transitions can exchange energy. Either they can absorb or radiate away photons. Okay, bound transition is like basically absorption or emission lines, where the electron jumps between two bound states, and one can compute what is the probability of absorption and emission. That will tell you how efficiently a given transition can be used to exchange energy between matter and radiation. Of course, you have to also remember, not necessarily all atoms will absorb or emit, but even if few atoms are involved in this interaction with photons, then the interaction between atoms will also exchange energy. So this is nice set of environment where photon interacts with some particle interacts with particles, and particle emits photon. So you have to have a soup of matter particle interactions, and one has to find out what is the effective way of doing it. So one way of doing is brute force. You take each volume, you can calculate how much times the scattering will occur, how much times absorption will occur, how much time ionization will occur, how much time recombination will occur. Or we can set up something like equivalent opacity, or we can say like as if you will sum up all these things coming with a fitting function which you can use. So this is the kind of things people use when you do stellar structure. The given temperature, density, composition, one can write down what is known as effective optical depth, and you will have something known as Rosalind mean opacity. I will not go into this. As far as you are concerned, what you have to know is that radiative transport is the very efficient way of transporting energy created in the center to the outer regions. And this involves all sorts of physical processes which was taught to you by Dipankar in his 4-lecture course, right? All the processes, of course, magnetic field is not there, curvature radiation is not there, and some of these things may not be there, but rest of the photon interactions with atoms will be all present. So that's why astrophysics is amazingly interesting, because when you do physics, you will use one concept, right? If you are doing solid state physics, or if you are doing something else, you will be using one concept and one particular detail, right? Whereas when you do astrophysics, you will be doing nuclear physics, you will be doing all the radiative processes, you will be doing, soon you will see statistical mechanics and things like that. So that's why astrophysics is not a fundamental physics, but is exciting application, is applied physics. So we have to remember, this is one of the classic examples where one can do. Of course, you will ask me, of course, can I treat this problem like this? Here is a burner, I put some gas on top of the burner. It's like my cooker on top of a gas stove. Their radiation process is not the way you you cook your food, right? To cook your food, you do something else, or boil your water, you use something else. Can these processes occur here? So one of the interesting process which we always notice in the presence of gravity and temperature gradients is what is known as convection. Convection is usually you have some two layers and you lift some amount of gas against gravity, it goes up and comes down. In this process, this bubble which is going up can exchange energy, or it can change its configuration and come down. Okay, so this is, if you can churn like this over a characteristic length, you can actually sort of exchange energy between these two layers by the motion of the particles themselves. This is what is known as convection. Radiation particles don't move. Actually, the heat is transported through photons. So basically, density doesn't change much, right? So that is good news for maintaining, if you are thinking of maintaining hydrostatic equilibrium. Radiation is a nice thing, because as long as you don't change the temperature, you will be maintaining the beautiful whatever hydrostatic equilibrium you would have established. Let's now take a simple problem of convective motion and see what is the demand I have. Okay, we can let convection happen in a star, no problem. But convection means matter is moving up and down. But this motion, if the motion is going to change the radius at a density at a given radius, then it is going to defeat our purpose, because then what happens, there will be no stable, whatever you call hydrostatic equilibrium. Okay, so all these processes, whenever you talk of equilibrium, there are some time scales involved and some length scales involved, over which you are allowed to change, but the changes will not affect overall large scale equilibria you have set up. So convection can also occur over some length scales where things don't change that much, right? Okay, let's understand what is the requirement for convection. So let's consider this simple problem. I'm not going to derive equation, but I hope I will convince you when convection will occur in a region and what is the requirement for us so that the convective motion can be allowed in sun or allowed in any star. Okay, let's consider a layer. So this is some small portion of sun or small portion of star. So this is the inner part and this is the outer part. A radius goes this way. That means gravity goes this way. Gravitational force will pull this way. So let's have, this is a hydrostatic, is a stratified atmosphere where density is ρ1, pressure is P1, temperature is T1 here. This is ρ2, P2, T2. And if you think of a situation like our sun, the things are going down like this. So temperature will be higher here, temperature will be lower here, density will be higher here, density will be lower here. Okay. So now what you do is that, suppose you take a small amount of fluid element in this atmosphere. Okay. Suddenly it has slightly more density. So you can define the new density as rho prime and P prime. So what happens here? This is a stratified atmosphere. I find a small fluid which has slightly more density and pressure. So now look at this point. This point has more. This point is not at the same physical situation like this, because of which what is going to happen is that the pressure here is more. So this guy will try to go up. Okay, this is basic idea of whatever we call convection. This guy keeps going up. So you can think of like a fluid, when it goes up, it can, for example, since it is going through a denser, a rarer medium, it can start expanding. Okay, that means when a fluid moves, fluid is allowed to expand freely, its density can change, right? Pressure can change. So let's imagine that it goes to another location here. By the time it reaches here, I fine-tune my problem in such a way, the pressure it reaches matches the pressure here. Okay, P2 prime become equal to P2. That means now this guy will set up in pressure equilibrium with the surrounding medium. This is a hypothetical problem. I can always make it happen. But now, having reached the same pressure, what is the density this gas will have? This I cannot say easily. Why? Because you know that if I take a gas and allow it to expand, what happens to its density or what happens to its temperature is purely depends on whatever is the equation of state. Okay, if you just expand and fix the volume, you can say what is the density change. But what we are saying here, I allow the gas to expand to a pressure. It goes to a particular pressure P2. Okay, so to reach that pressure, the combination of density and temperature should match with the density temperature outside, right? ρ2 T2. So what will be the final temperature will depend upon what is the nature of the fluid. Suppose if this fluid is an isothermal, it has an isothermal equation of state, the temperature will not change. The density is the only thing which will fix the pressure. Okay. Whereas if it is adiabatic equation of state, temperature will adjust itself, right? So that you will find the pressure will be decided by both density and temperature. What it means is that when the fluid comes here, when the pressures are matching, it doesn't mean that the density will match, right? Okay, fine. Pressures are matched, density is not matching. Now you can ask what will happen. If this ρ2 prime is much lower than ρ2 outside for some reason, ρ2 prime is lower than ρ2, then what will happen? So at the same, you can think of like this fluid in equilibrium, hydrostatic equilibrium, and hydrostatic equilibrium as a ρ term. This ρ is smaller than this guy because this guy is already in hydrostatic equilibrium. If you want this fluid to be also in hydrostatic equilibrium with the rest of the star, this guy's ρ2 prime should be equal to ρ2. If ρ2 prime is smaller, it will not be in hydrostatic equilibrium here, and it will start moving outwards. Okay, so this situation is not good for us because you create some perturbation in the fluid, because of which the fluid started moving up, but it is never going to be in any particular radius which is going to be in some sort of pressure equilibrium, or at least the radius of my interest, it is not going to be in pressure equilibrium. This guy will just go away, up. On the other hand, if your equation of state will make this ρ2 prime greater than ρ2, then what will happen? This guy will now suddenly have the same pressure, but the density is higher. It will start moving down. Of course, it can move down since the property of the gas is such that when it comes here, it will come back to ρ1 prime, p1 prime. It's clear that you can have material going up and down like this. How you will do it is depending upon several quantities. One is that what is the length scale over which you are happy to allow the convection to take place, so that your equation of state, your hydrostatic equilibrium is not violated. The length scale over which you can allow particle to move. Because the other way of understanding is that in a given temperature, particles are always moving. That doesn't change because that scale over which your interest in particle motions is different from the scale over which you will calculate pressure. Similarly, the scale over which you will set up hydrostatic equilibrium, stable hydrostatic equilibrium, will set up what is the range over which convection can be allowed without destroying the whatever you call hydrostatic equilibrium. Within that region, only few kinds of things are allowed, in the sense that only fluid with correct equation of state will have this thing going around. So I set up a particular length scale. That length scale will set up what is the pressure gradient allowed by the hydrostatic equilibrium, and then I will find out what will be the pressure difference. I will find if the fluid is allowed to go from bottom to top. This given by the equation of state. This pressure gradient is given by the hydrostatic equilibrium. That means you can clearly see there is a nice tight constraint on how much convection you can have in the region. Okay, so in principle, convective motions are very, very small in the central regions. Usually, people believe, for example, if you take sun, this is the picture you will see in typical solar things. But usually, what happens is that outer regions will have some convective zones, and inner region, you people believe that radiation goes out. Of course, this is all pictures. In reality, each star, each situation, you have to make sure that these kind of things you work out. For example, instead of hydrogen burning in the center, if helium burning or something else starts, what will happen to the energy? You have to self-consistently do. I will not do in this class. But just for summary, we understood what is the requirement for energy transport, tight coupling between particle and photon when the photon transport occurs. Photon transport is usually a happy situation because particles don't move, and most of the time you are remaining in hydrostatic equilibrium. Okay, when you are in convection, again you can set up convection in such a way that you will not destroy hydrostatic equilibrium over long periods of time, and so that you destroy the whole star's configuration itself. And the requirement is you set up length scale. Over the length scale, you calculate what is the pressure gradient allowed by the your hydrostatic equilibrium. Then you figure out, given equation of state in that region, whether you will have convection or not. Okay, requirement of convection is that the density, whatever I said, the d rho by dr will be sort of somehow related or more than this whatever you call hydrostatic equilibrium gradient, pressure gradients. Okay, I think this is sufficient for you to follow. If you are really serious about it, I can give you references. You write to me, I can give you follow-up references. So now we have set up. You know that how a star can work. You can form nuclear reaction and things like that. Let's see what is the bigger picture. Now I switch off from theory. Little bit of observational thing we will look at, and we'll come back. And this plot, I have seen that two of my colleagues have shown you already, so I will not spend much time on it. But let's understand physics-wise how to understand this picture. So what happens in astrophysics is that whenever you observe a new set of objects, if the objects have varied parameters, one thing people will do is that plot x versus y. Suppose you have a particle, if you have an object which has a property called x and property called y, you plot x versus y. If x versus y is a scatter plot because you don't see a line or you don't see a pattern, then you say that the quantity x and y, which we measure from the object, is uncorrelated, meaning that there is no connection between them. Whereas if you find some kind of trends, then it becomes interesting that maybe there is an underlying physics which controls the property of these objects. This is how you go ahead. Okay. What is plotted here, which you have seen twice, at least thrice, I can think of from your previous lectures. You plot luminosity along y-axis and temperature, surface temperature along x-axis of the stars. You take large number of stars and calculate luminosity and calculate the temperature and plot against each other, and you find this curve. And the curve has a straight line, which is called main sequence, and you also see something. So these guys are not populated all over the place, and it seems that the stars lie in a particular region. So for our purpose, a trend in a population could be an evolutionary sequence. For example, this can happen like this. So whatever you have plotted here, you can think of like this is a parameter of the star. For example, we said like if it is 10 to the 3 Kelvin or 10 to the 4 Kelvin is the temperature of the star, which means that depending upon the temperature, the luminosity may be different. And the star need not be at the same temperature and luminosity throughout its lifetime. It can keep on changing its luminosity, because of which the temperature can change, which may mean that whatever we are seeing here could be related to the time a star spent in a given parameter space. I'm sure that you don't follow it. At least some of you will not follow it. Let's take a real life example. Okay. I'm living in Pune, so I'm aware of this this highway between Pune and Mumbai. This is one of the first highways created, expressway. Suppose let's make an example that I send cars with a constant interval. I release one car per unit minute per second or per minute or 10 minutes. Every 10 minutes I release a car in Pune, and I instruct a driver to travel. Whenever he drives, the car should be at 80 km per hour. That is the speed at which the car should go. I release the car continuously, right? Though cars are going, some car would have reached Mumbai, and once it reaches the Mumbai, it goes away from my horizon. I put a camera in the sky and take a snapshot of cars. What you will find is that in the road, cars are EQ spaced. Okay, is it correct or not? Right. Now what we do is that the government has set up toll. Okay. Now if I do the same exercise with couple of tolls along the route, you will find one thing is that the cars are traveling at 80 km per hour, whereas when they see a booth, they have to stop. Okay. So if you take a snapshot, suddenly I find that there is a huge accumulation of cars, star and car. Okay. A huge accumulation of cars at the locations where it is to be stopped to pay toll. So it's exactly like this. So the density of cars is now proportional to the extra time they spend somewhere, right? All the cars are made to spend some time there. Okay. Car, star, car, I confused, but you guys understood this. This is exactly like this. So this is the situation you have to be. And I will now try to guide you through so some physical picture so that we will understand how you can understand this one, right? I'm not going to do. Let's understand a simple way of navigating through this figure. X-axis is temperature, and usually temperature goes this way. That means the highest temperature is here, lowest temperature is here. That is the way people plotted. Luminosity goes this way. The brightest star will be here, and the faintest star will be here. Okay. Now let's understand what is luminosity. Luminosity is nothing but 4 pi r square sigma t to the power 4. What is here? It is t. Okay. If I fix constant surface, right? I fix the size of the star to be same, and if I make star to have different temperature, how the curve will look like? Okay, here the luminosity will be more, here the luminosity will be less, the slope will be t cube. Okay, because here is t, here is t to the power 4, and you will have a slope like this. Okay, correct? So typically, if you take all the stars to be of the same size, then you should find, you expect you are plotting t cube versus t to the power 4 versus t. That's the relation you have to see. The first thing you realize is that if you go and imagine that these are different stars, do they satisfy that kind of relationship? That means the size being same, only temperature being different. you can find out that that is not the case. I will leave it as an exercise for you to take these plots from anywhere. Just see whether the slope is consistent. This is temperature here, this is luminosity here. You understood that this is the equation connecting between these two. If R is same for all stars, you should have this thing. So first thing you realize is that the radius of all the stars you see need not be same. If radius of stars need not be same, immediate conclusion is that all the stars you see in the sky will have different sizes, which on the consequently you can also say they should have different masses. This is the first thing we understand. Stars are not typically like sun. They may have masses much more than sun or much less than sun, which also means that they can have different sizes. Okay. Now, what about temperature? We'll come to in few minutes. We cannot make anything. It is possible that all stars can have same temperature but different sizes. We don't know. Let's come to it later. Okay. Or that part is actually I can go ahead with it because that part is covered by Ranjan. Ranjan showed you the spectrum, black body spectrum, and he also showed the temperature of the stars are not same, right? That we used in the previous plot here. The temperatures are not same because this is coming from the fact that you are fitting the black body spectrum to the curves. Okay, let me now restate whatever I wanted to state. We know temperatures of the stars are not same. We now know that the radius of the stars are not same, which means the masses are not same. So you have parameters, we have distributions of mass, distributions of temperature, and distributions of sizes. Okay, good. Now let's consider a hypothetical scenario. I have a star. The star is formed and it is set to with a radius and temperature, and it is going to be there forever. Meaning it is going to shine like this. This is what we want, right? Look at sun. Sun, we said that it is hydrogen burning. Hydrogen burning will take huge amount of time. So it can stay in the same luminosity and same temperature. Then what happens? It will stay here. Okay. Here means it's a point I have chosen. So when a star lives in a steady state, it will not move in this plot. You agree? Which means that in any of the star which is put here, if it is in pure hydrostatic equilibrium, it will remain here forever. So that means the star here will not move here. Okay? Right. That's the first point. So when a star, as long as a star can generate a uniform amount of energy, right, at a uniform rate at which it creates energy, it can stay in the same plane for a long period of time. Now let's do some simple tricks. I somehow make the star expand or contract isothermally. You understand what it means? I let the star to expand. That means I'm going to say that, okay, you now violate the hydrostatic equilibrium. Either you expand or contract. Then what happens? The temperature is not going to change because it is hydrostatic equilibrium. The star will become either more luminous or less luminous. So this will move along this line in this diagram, this HR diagram. A star which is expanding isothermally will move up and down, right? Expand or compress, depending upon whether it is expanding or compressing, it will do like this. When it expands, it will be more luminous. When it compresses, it will be less luminous, as long as it is isothermal. Correct? Okay. Let's now consider a situation. I'm going to now change the temperature. I'm going to allow that temperature also to change. Okay. So now let's take this example. I take the star, allow it to expand in size. Okay. The star expands in size. Then what happens? And I can say that, okay, when you are expanding in size, you cool down. Okay. Then what happens? The star expands and it cools down. That means because of expansion, it is going to have, because of cooling, let's say, cooling, it will move in this direction. Because it is expanding, the radius is increasing, okay, it can start moving in this direction, okay. If you can increase in surface area while small amount of decrease in temperature will make it go in this way. Of course, you can play with the area kind of thing and see like, so I'm looking at a generic solutions where the expansion gives you some sort of higher luminosity and the temperature decreases. So this is interesting. Okay, the star become bigger luminous, but if you take the spectrum, the temperature will look lower. Okay. On the contrary, I make the star compress to a smaller area. Okay. So, and suppose if it is adiabatic kind of star, the temperature will go up. Okay. Then you see that this will move in this direction. So it's absolutely interesting. The way you will read HR diagram is that I go to a point. The fact that I see a point means like this star may be living in this point for long periods of time, because that is what its hydrostatic equilibrium will do. For some reason, I ask the star to let it violate hydrostatic equilibrium. It can violate in various ways. If it is going to remain in constant temperature, it will go up in this plane. If it is going to increase its surface while decreasing its temperature, it will go like this. If it is going to decrease its surface and increase in temperature, it will go like this. So it's clear that in a first order, you can understand few things by putting star here and make it stable. I can go from here to different parts by allowing it to violate hydrostatic equilibrium. This is a simple thing. So the Hertzsprung-Russell diagram can be understood as part of stellar evolution itself, right? The main sequence, the so-called main sequence, is the region where star will spend maximum amount of time. That is the understanding here. Okay, so I'm not going to teach it like astronomy, right? So I have to do it astrophysics. Let's do like this. So you understood how this will be moving in this. So now let's start with formation of stars. Now I'm going to start from the first principle. What is a star, right? Okay, I have 30 minutes, so I have to go slightly faster, right? Otherwise, I will have 2 minutes. Okay, the first question we want to ask is the following. So I want to make a star. Star is nothing but gas clumps. So I will start with a gas clump. And once you put a gas clump, there are two forces in the gas clump. One is the self-gravity, the gravity of all the particles together. And the second thing is the pressure. The condition required for producing, the condition required for producing a star is given by what is known as Jeans instability. What basically you are saying is that if I let the star collapse on its own, the time scale at which the outer part of the gas will fall into the center can be written as what is known as free fall time. That will go as 1 over root 0. And we have to make sure that the time required for the whole mass to fall into the center, which is called free fall time, is much shorter than the sound crossing time. Means like the time it takes for sound to go from center to the outer part. Because if there is a disturbance, you will know there is a disturbance only when you communicate that disturbance to every part of the gas. So that can happen. Any disturbance will travel with speed of sound. So this condition, if you satisfy, that means the time required for free fall is shorter than the sound crossing time, where Rj is the size of the cloud. This I call it as Jeans length afterwards. So there is a length scale R for the cloud. Cs is the sound speed. If this is the sound crossing time, if it is larger than 1 over root 0, I'm talking about constant density sphere, and then you will see that there will be a collapse. Collapse means what? So this means that your gravity will win over the gas, and the gas will now going to be compressed into a smaller and smaller density, because we have to reach a density where you can set up nuclear reactions. So what is Cs? Cs is sound speed, and you know that Cs is nothing but root of gamma p by rho. What is gamma? Gamma is the ratio of specific heat, Cp by Cv. And if in an ideal gas, you can write down as gamma kT by m. I'm going to assume that mass now will be per unit volume. I can write down like this, and this is nothing but whatever for purely hydrogen atom case. So now what is mass of this star, which will be, you can write down what is the requirement of mass so that it will become unstable and start collapsing. This goes by the name Jeans mass. We can write down as 4 by 3 pi r cube into rho naught is the initial density, and Rj can be written from Rj will be something like this, right? So you can from here Rj equal to, but you have to satisfy the condition that Rj should be more than this for a collapse. Okay, Mj is the mass at which it will be stable. If mass is more than Mj, it will collapse. Now you can substitute Rj from here and substitute this guy here, and you can get an expression for Jeans criteria. So as long as the core density in a region satisfy this condition and the temperature density relationship is satisfy this condition, if the mass is more than this, the gas will collapse. Of course, when the thing doesn't stop when the gas collapses, when the gas collapses, basically what happens is that you are going to compress the gas. When you compress the gas will pressure will change, the pressure will go up, so it will resist the further compression. If you really want to compress the gas to the very low volume, at every stage you have to satisfy this Jeans criteria, means the mass should be more than the Jeans mass. The way you will achieve, the densities keep on increasing. You can't play with the density, but you have to play with the temperature. So when you compress, you have to make sure that the temperature decreases. The way you will do is that whatever extra energy per unit volume given by the compression should be removed by the radiation. So as long as the gas can keep on throwing energy gain, this is the expression I told you. You remember we did in the previous class. Gravitational potential energy can be radiated away. If you can do that, if you can radiate away the extra energy you are getting from the compression, the gas will cool. Again, at that instant, it will satisfy this Jeans criteria required for compression. So you can't keep on compressing the gas to a much, much slower volume as long as you can create energy, and the energy creates photon, and photons can leave the system. You will stop this process when the photons becomes optically thick, the region become optically thick to photon, then the photon beginning to build up, energy beginning to build up. At some stage, this guy will now collapse to, this guy will start a nuclear reaction in the center. Okay, so let's understand what exactly will happen to these stars. Okay, I will skip this slide because this slide I wanted to show you that I have already explained. You don't form stars with one mass, you will form stars over a range of masses, and the probability distribution is given by initial mass function. Okay, so this need not be related to what I am teaching now. So I will come back to it in the afternoon. So that's why I'm skipping. Don't worry, this will be taught to you in the afternoon. Okay, now let's look at this condition and see what happens in the luminosity temperature relation. Okay, so this is the luminosity temperature relation. Let me start with a star of some. Let me start with a region. Suppose I have some gas. Gas has some temperature and it has some density, right? I am going to this guy satisfy whatever we call Jeans condition. It is going to get compressed. So what I am doing, I am compressing the gas. When it is compressed, the area is going to reduce. But we said that in order for efficient compression, this guy has to go through isothermal compression. So in the initial stage of star formation, the gas will go through isothermal compression. That means the radiation emitted by this will follow this track. Remember what happens in isothermal compression? Temperature does not change. Since temperature does not change, the luminosity will decrease because the area is shrinking. Correct? So the protostars will follow this track in the luminosity temperature diagram, right? Up to the point where the core is optically thick. When the core becomes optically thick, the radiation cannot escape now. So if you keep compressing, what will happen is that a compression will lead to some sort of buildup of temperature. So the temperature will keep on increasing. If the buildup of temperature sort of does not, it may change little bit of the area, but mainly this is the situation. Temperature builds up in the core, right? And if the temperature buildup is sufficient to create hydrogen fusion, then you will create hydrogen fusion, right? So the star will start from somewhere. The protostar will travel this trajectory and settle down to a hydrogen burning stage. Of course, now we are experts. When hydrogen burning stage happens, if you trigger hydrogen, what did we say? We need only small fraction of hydrogen to form star, to generate the amount of energy we see. But this amount of energy is sufficient and this process is slow. Why it is slow? Please remember, it is slow because we have to convert one proton into a neutron. That is a bottleneck, because of which hydrogen burning cannot be done in a hurry. So once you start with a protostar, bring it to hydrogen burning, this guy will live there forever. For example, our sun is living for 10 to the 9 years at the same location. Okay, that's why this part, we start from here to here, this track a star follows is known as Hayashi tracks. Okay, actually this is I gave a very simplified picture. You have to also use some amount of convection to transport energy, but the basic picture you understood, right? I'm keep on compressing all the extra energy I have to radiate away. That is the basic principle, so that the temperature doesn't change. This is the thing, and to come. So you are now set for what is how the protostar is formed, and this goes by the name. Okay, the forbidden zone means like if you start from here, you will never reach the situation where you will be able. The compression is good enough to form stars. Of course, you can ask, why should I start from one gas particle, gas cloud here? I could start from gas clouds of different sizes and different initial condition. This is what you do here. If you start with different, this is what is shown here. So this is a star which will start with different masses. If you have started with 100 solar mass kind of thing, so it will immediately reach the small amount of compression can lead to nuclear fusion in the center. So this is interesting. Depending upon what is the initial stage, the Hayashi track will be different. Okay, the Hayashi track will lead to different locations in the luminosity surface temperature diagram. But wherever Hayashi track stops, this is what is known as zero main sequence star. That means this is the place where you set up hydrogen burning. You guys are with me, and now this basically explains. We'll go back here. This basically explains my whatever I call this HR diagram. So this is main sequence. How do you understand this main sequence? This line is because this is the place the star protostars which would have started from somewhere here as whatever you call cloud, it would have moved like this and landed here. You follow me? It would have started somewhere here, moved like this and landed here. Something might have moved like this and landed here. So all these are basically stars which are going through hydrogen burning. So this main sequence, whenever you see main sequence, we can say the most dominant energy production here is the hydrogen burning stage. Okay, I didn't put any equation. I follow simple logic, and you guys are with me now. You understand what is a protostar, what is the requirement for protostar formation. This is Jeans criteria. Okay, this picture depicts various things I explained to you. Core collapse, the guy gets heated up. It radiates away some amount of energy in black body radiation or whatever form you can think of. Okay, but there is slight complication compared to whatever I explained to you, because when I was explaining to you, I forgot about the fact that there could be angular momentum associated with the gas which is collapsing. If there is angular momentum, you have to also worry about the conservation of angular momentum, or you have to somehow remove the angular momentum from the collapsing gas. This will be done with the production of jet and disks. Actually, the star doesn't collapse like the way I told you. The star will form. There will be disks formed around the stars, and this formation is extremely important, because these disks, the matter in the disk will be thrown out at some stage, and this physics of this disk formation, what happened in the disk, leads to planet formation, which I will not go into detail in this lecture, and somebody may tell you, or you can read it out. Okay. So now we have formed stars. Sorry, we have formed clumps. We understood when it will become star, and we also followed the clumps evolution. Now you found it has formed stars, and when it is in the star, I have already taught you the physics, which is hydrogen burning, PP chain reaction, which goes on, and then what happens? Now let's go to the next stage. Before going to the PP chain reaction, we can say what happens to the main sequence itself. Is there any physics I can follow in the main sequence? Okay. So now what? Now we can do some. I want to avoid teaching you theory, so we can do a little bit of observational thing. So what people found, something interesting. People calculate the luminosity of stars in the main sequence, calculate mass of the stars, and they plotted against each other, and it's a nice line. It's an amazing line. Actually, it's one of the tightest lines one can see in astrophysics. and you can write down a luminosity of any star can now write down in terms of luminosity of the sun and mass of the sun through this reaction, this relation. That means more the luminosity, the mass seems to be higher. Okay. So what is the consequence of this? Which means it's interesting. Let's just reiterate what we are saying. You are now in HR diagram. We say that the stars can come from anywhere here, and all these stars are in main sequence with different temperatures, outer temperatures, and main sequence with different luminosity. What one is finding observationally is that if the luminosity is higher, the star tend to have more mass and it tend to have more temperature. Of course, it is not very alarming to you. In the first lecture, I showed you that when you look at the core pressure is a function of mass, right? Remember 2/3, right? To the power 2/3. So which means that it is obvious that when their mass is more, core pressure will be more. Okay. When core pressure is more, it can sustain whatever gravity mass. This is the picture we have. Now we have a new information given to us. New information given to us is that the luminosity is higher for stars with higher mass. Let's see what is the consequence of that. So let's go back to my equation. Tau, time taken for a star to go through hydrogen burning is given by this equation, you remember? Now if I say the hydrogen burning stage is related to main sequence, you can now write down, you can now call the time as the time up to which a star will spend in the main sequence. You can now remember this equation. It is E by L, and this is the equation I wrote down. Okay. So this equation now you can modify. Now you write down L as L star blah blah. Okay, you can do this. And this number, you remember, this number we have written down for solar mass. Because one solar mass, I found out how much time it takes. So that one solar mass, if you remember, we take something like 10 to the 10 years. Okay. So now I have not done anything different, right? This is the same thing. I have just plugged into this. Now this equation will be something like this. I mean, this is important for you to realize. Main sequence lifetime is inversely proportional to mass to the power minus 5/2. It's amazing. I think you can now look at it interestingly, what its implication. The implication is the following. How long a star will stay in the hydrogen burning stage depends on its mass. More its mass, it will remain for a shorter period of time. But shorter is very short, right? You see, just for example, if I put 10 solar mass of, if I take a 10 solar mass of star, if sun lives for 10 to the 10 years, a star which is just 10 times massive than sun will live only 3 10 to the 7 years. This is an important lesson we have to learn, that more massive stars live shorter than the less massive stars. The fact that the sun is still staying there tells you that it still has some hydrogen in its center which can burn. Okay, so you understood this. So what is the consequence of that? I think I can skip this because star spectra has been shown to you by I think Ranjan Gupta. So I will not spend these classes of stars. Okay, but there is some physics involved here. Okay, now let's look at the interesting part. So if you look at Hertzsprung result diagram of a cluster, suppose you take a star cluster. For each star cluster is collection of stars. They are at the same distance to us. We can actually look at each stars. Now plot the whatever you call temperature luminosity diagram, and this is like this. And usually you find that for some groups, this curve goes like this. So the curve is main sequence, and then it turns around and goes like this. So it is clear that at some luminosity or some temperature and some luminosity, the main sequence stops. Correct? This is main sequence. It should have continued. In some set of star clusters, it continues forever. In some of them, it turns around. So now let's put together all the points we understood. A star will be in the main sequence as long as it is burning hydrogen. It leaves the main sequence when hydrogen burning stops. So let's clearly we can say, in this particular case, the main sequence, the stars stay up to main sequence up to this temperature or up to this luminosity. Okay. In some other case, it is living up to larger luminosities. So, which means that in this particular M67, we don't have stars which have large main sequence lifetime. What does it mean? Very simple. Main sequence lifetime depends on what? Mass of the stars. So here, in this particular case, if you follow this, right, there is no massive star. Whereas in this case, okay, wait a minute. In this case, where I go to NGC 2362, there are large number of massive stars. What is the meaning of that? Meaning is very simple. This cluster should be older, because if it is younger, you would have seen all these stars. Why you don't see the stars when the cluster is older? Because we just now saw the lifetime of main sequence stars are very small when it is very massive. So if the star cluster is older, then massive stars would have disappeared, or which would have moved out of, they would not have disappeared, they would have moved out of this what you call main sequence. Okay. So when you find a main sequence turnaround, this is known as main sequence turnaround, that sets what is the mass of the star which is still going through the hydrogen burning stage. And we know, given the mass, we know what is the age of that star. So the age of the cluster should be more than that age of the star. Okay. So you can measure the age of star clusters by just plotting this whatever HR diagram and actually locating where the turnaround occurs. Okay. So this is very important, and this is one of the consequences of understanding main sequence. So because of which we can now say that the main sequence turnaround will give you the lifetime of the stars, star clusters, and this you can use to put constraint on our universe itself. The age of a star cluster in our galaxy should be more than the age of the universe itself. Okay, so that's why measuring the oldest star cluster is important for our purpose. Okay. So I will go through this slide, and then I will I have to stop. Maybe I will stop at exactly at 11, because I will take 5 more minutes and I can take questions for 10 minutes. Okay. So basically this is what is happening, and now let us look at what happens to the star which leaves this main sequence. What is the idea of leaving the main sequence? Idea of leaving the main sequence means that hydrogen burning stops. So let's now look at physics of a simple region where I am in hydrostatic equilibrium. Okay, fine. Now hydrostatic equilibrium is maintained because I am generating energy in the center, and that maintains pressure, and pressure that generates pressure, and that maintains the whole thing. So suppose for some reason I suddenly stop hydrogen burning. Then what happens? The initial part, internal part, the core part, there is no energy generation. That means the gravity has a free ride. Okay. Now, before I go any further, you will tell me now, oh, I have helium there, because I burn all the hydrogen. When I'm going to stop means I have converted all whatever maximum amount of hydrogen I have into helium. Why can't I now fuse helium and generate energy? Of course, you are going to do, but you remember, to fuse helium, I have to go to much higher temperature. This is what I showed you in the last class. So what happens is that I have a situation where I burnt out all the hydrogen. I have only helium, but the helium cannot form carbon, right? So what happens? It will just, the core will start collapsing. Whereas the outer part will take some time to realize that the core is collapsing, because you know that there is diffusion which is taking place. It has some time to communicate outside, right? It has some time involved. So the core collapse in this region. When core collapse, you have to sort of you have to wait till the core reaches the density temperature required to trigger helium. Okay, but the helium burning can take place very fast compared to hydrogen burning. This is what we learned. Once you start helium burning, what happens? Now you have a mass radius set up for you, more or less. That is not destroyed, because the core collapse is much more rapid. It won't destroy that much of the star, original star. But the core is now generating energy much faster compared to the previous stage. So if you want to keep hydrostatic equilibrium, the star has to expand. In fact, the helium burning finishes in such a rapid. Helium burning takes place at a high speed. The star started expanding very rapidly. Okay, what is the consequence? When something expands very rapidly, the density goes down everywhere. So again, the ability to form helium burning will stop. So it's very interesting. So this is just an example of what happens. So you start some new nuclear reaction in the center, which creates extra pressure. So the guy will start expanding. When it expands, your nuclear reaction stops. That means when it is expanding, you are not supplying same amount of heat you have been supplying before. That means the temperature will fall. So it's very interesting. After when some star leaves this one, depending upon what is the core burning as well as what is the expansion, they will start going into this. It will start expanding, but it is cooling, so luminosity will increase, but the temperature will decrease. Of course, this guy will not go forever. At some stage, the gas will, the gravity will win over, and it will bring back this guy here. This sequence can continue till you can maintain some amount of core nuclear burning. Okay, this is the simplest way of explaining. So this stage where the star is bloated to a very large size, but slightly lower temperature compared to its main sequence temperature, is what is known as giant phase. And you understand how the giant phases occur. And when you run out of fuel, then this cycle cannot last forever. It can go into, okay, so I'll stop here probably. Okay, I'll just explain this part and I'll stop here. And maybe I will finish this lecture in the afternoon and take up ISM, which I will do. So let's just summarize what we have achieved. What we have achieved is that we understood how to form a star starting from a cloud, and a cloud will collapse and it will go through what is known as Hayashi tracks. And if the cloud initial mass is in the good ballpark, the collapsing region will reach temperature density in the core such a way that you can trigger nuclear reaction, and it will be in the main sequence. When it is in the main sequence, it will remain in main sequence as long as hydrogen burning continues. When the hydrogen fuel is stopped, it will go to the helium burning stage. And helium burning stage is interesting because before going into helium burning, you have to compress the core to the much higher density. You will compress the core to the higher density. When you manage to compress and start the helium reaction, the reaction takes place much more rapidly, because of which the star will expand, because hydrostatic equilibrium will be achieved at a much larger radius. But when you start expanding, your number density in the core goes down, so you have to stop the nuclear reaction. So the star will expand up to something and come back to whatever is the original density till it compresses to start another nuclear reaction. So this cycle can go till you reach a stage where the compression cannot produce nuclear reaction of the material in the center. When it happens, you push the star to its final stages. We'll explain this in the next class. But while doing this guy will go through this region. Since this region, these time scales are much smaller than the time scale involved, you don't find large number of stars occupying this space. Okay, that is the point, right? Most of the stars are here. When they leave, they go through this plot very rapidly. So when you take a snapshot, you will catch them not in the same place, but you will catch them all over the place. So since you are dispersing these stars, so the density of stars in the HR diagram is very small. Okay. I hope I conveyed the basic idea behind the stellar structure and what happens, what physics goes on here. I have two things I wanted to explain to you. One is related to the CFID variables. And probably I heard that you, Shomak, spent some time, and also to end stages of the star. This is what I have. This figure also I saw Shomak had put it. So I will explain these three, then we will move on to interstellar medium in the afternoon. So I will stop my talk here and take your questions.
Okay, thanks, Anand. Very interesting lecture. There were many questions today. So please raise your hands if you had a question. I don't think we'll have time to answer all of them because we are running slightly late, but we'll see as many as we can do, and then we'll find a way for you to communicate. One question that keeps coming up is, are there any reference books that you can suggest? Maybe if you can just add them to some of your slides, we can upload them.
Okay, I can do that.
Yeah. Okay. So now there are a few people who had more than one question. So I will come to you in a bit. Let me first take a question from somebody who did not have their mic working. So two people had the same question essentially, Vaibhavi Gavas and Rahul Priyadarshan. They are asking, why are we considering the sound crossing time to compare with free fall time when you do the Jeans instability criterion?
Okay, because we are considering perturbations perturbation traveling in the material, right? If you take a gas, the fastest rate at which you can communicate the disturbance is by sound speed, and that's why you do with sound speed.
Okay. So for people who had two questions, I would request you to ask first one question, whichever one you would like, and then if there is time, we'll come back to your second question. Okay. So first, let's have Unix Sengupta. I've unmuted you. Go ahead.
Hello, sir. Good morning. Sir, the question which I got is actually from the first of the slides that you just explained today. During the convection process of energy transfer, which happens in the stars. Sir, during that process, we had a effect or had a function of gravity in there, right?
Yeah.
Gravity is taking a role in there. So how is this process effective in case of white dwarfs or neutron stars where the gravity is excessively high or gravity plays a major role? How is this process helpful in that case?
I don't think convection takes place in the core of. I don't think this is like a solid, right? If you, my understanding of white dwarf is like it is more like a rock, meaning like in the sense of a solid kind of thing, right? I don't think convection and all takes place in course of white dwarf or something. I'm not aware of this thing. So you can think of, see, I understand them like the free particles, electrons settling into some sort of allowed levels allowed for it to settle down. It's like that's what it is, right? There is no nuclear reaction, there is no radiation which goes away. And I think it radiates like a black body. Some amount of radiation comes from white dwarf because it releases the potential energy. And I don't think convections and all take place at those densities. I don't think so. But I'm not an expert in white dwarf physics.
Okay, so we have a question from Himadri Saha. Again, please ask one of your questions. I've unmuted you.
So my question is that how can we characterize brown dwarfs using that Hayashi trap? Because we know that it may go acyclic compression, but it will not start hydrogen burning.
Yeah. I think that is the I gave you a very simple picture, right? This is what is the picture, right? When so you don't join the main sequence. I think these guys will stay slightly above, right? This subdwarfs and main dwarfs, they will never reach the main sequence. They will stay slightly above or below. Actually, they will be slightly less luminous for the.
Okay.
I just wanted to tell you that, okay, HR diagram is good, but when you are actually looking at the physics, you will just solve the hydrostatic equilibrium and see like whether you can sustain it. I mean, that is the best way to understand. And subdwarfs and brown dwarfs, you don't reach that kind of stability, and that's it. For example, Jupiter, for example, just failed. I think.
Okay, so we have one question from Madhusudan Purohit, mic not working. So I will read it out. Is it necessary that there will always be a planet formation along with star formation? Is there any limit on angular momentum of the gas disk for the star to form?
Okay, I think first I will ask the second question. I will answer the second question first. See, basically, the way I understand this, okay, is the following. Suppose you take mass of the star, and you will hear from me in the afternoon about the interstellar medium between stars and between stars in our galaxy. So you are going to collect gas from some radius into form this star. Okay, so our galaxy is rotating, and a lot of bulk motions are there in that radius of interest, right? A differential rotation as well as random motions. So this will give you a angular momentum. Total initial angular momentum comes from the star, from a gas from which I am going to form star. The distribution in space will give me what is the initial angular momentum I have. The final angular momentum is what we see in sun. We know how fast sun is rotating or any other star is rotating. Okay, so the idea behind this, the requirement is to see how much the two constraint. One is the constraint comes from where I am scooping up the gas, right, from the interstellar medium. Second thing is that what is the final product. So there is no unique answer. What is the angular momentum, maximum angular momentum, minimum angular momentum? That is depending upon what my aim is to produce. Okay, that is the thing. Second thing related to planet formation, I think it is if you look at disk formation is very natural. Meaning all stars will form with disk. That is very natural, and people are seeing that the protostars have disks, gas disks around them. Now the question is, will you form planets in them? It seems that people are able to form planets in models. Okay, and it seems to be that is one of the efficient way of removing angular momentum from the initial collapsing gas. If you have planets, or you may not form planets, but definitely people form a lot of solid particles. Okay, so you have to form not only planets, right? You have to form asteroids. You have to form all the material which is going in between our planets, right? So forming material in the disk is more natural. Whether it will become a planet or not is I'm not sure. It's up to the models, but people think that it can become.
Okay. So next question is from Aparna KP. I've unmuted you. Go ahead.
Sir, my question is regarding the HR diagram that you showed of the star clusters.
Yeah.
The question is, some star clusters like the M41 had a gap like after the turnoff, while some like M67 had a smooth curve, the evolutionary stage. Does it have any physical interpretation?
Yeah, it has a physical interpretation because you just see that M11 and M41. I hope you are seeing the slide. In the M11 and M41 has much more luminosity compared to M67. What does it mean? It means that you have to make this star much bigger, right?
Yeah. Yes.
Because the luminosity. So this may be coming from a bigger star to start with. So that is the meaning. Because one slide I skipped is that when you form stars, you will always form large number of low mass stars and less number of high mass stars. Okay, because of which as you go down in this turnaround points goes down, the number of stars leaving will be less. Because you form, if you are here, there's a number of stars leaving here will be more. Number of stars with high mass leaving will be much less here. So you have to clearly. So as you go here, you will start finding lot more populations here, because then they can go up to much larger luminosities. When they go to much larger luminosities, they will also proceed much more in the nuclear reaction, because the core can see. These guys will stop with, for example, the carbon. See, some white dwarfs will be formed from here, so they won't proceed up to iron, because the nuclear reaction cannot proceed further, because given the mass, the core can never be pressure more than some value. So these stars will sustain once the carbon is formed. After carbon burning stops, it may not proceed much more than that. Okay, that's why you will not find somewhere here this cycle of going and coming, which I said will stop after some of them, which will stop after helium burning. Some of them it will stop after carbon burning. Some of them can go up to the stage where iron is formed in the core, right? Or iron or whatever, very heavy elements are formed. Those will go here because they have to be very massive. So that's why these young guys, you see, H plus X per se, which has something here. So this is very young, and it may have a very massive, what you call super giants. That's why these giants will have red giants and red super giants. And red super giants means it is coming from a star cluster which is very young. I hope you understood this. If you are very curious, I will suggest that if you are a physics student, these lectures are given to just initiate you, excite you into this field, but don't think that it is a final stage. It is, I would think that it's a 0 stage. You go back and start actually writing down equations, and there are books which gives you these codes. You can run and see where the tracks take you. Okay.
All right. We have one question from Vishwakanan. I've unmuted you. Go ahead.
Sir, can you hear me?
Yeah, of course.
Yeah, my question is about we have planetary, we have star forming regions where there are multiple stars formed from a single nebulae. How does the gene mass and the Hayashi tracks take different there? Because we have different types of stars forming from a same cloud.
Yeah. I think I've forgotten one thing. You have to understand if so, for example, if you take the same nebula, whatever cloud you are talking about, you can ask why can't this cloud become a single star, right? That is the question you have.
Yes, sir.
So basically what happens is that you have to introduce some amount of perturbations. When you introduce perturbations, if the cloud is very large, suppose you take that it takes 10 to the 4 years to go from one end of the cloud to the other end of the cloud. Okay. And
Yes,
if your perturbation in a small region, every place you can define a local gravity. Okay. There is no single gravity like this. For example, when we are in Earth, the gravity which is important is Earth's gravity for us, even though we are influenced by sun. Like that, for example, if you take a massive cloud, you create small perturbations where the sound crossing time there may be smaller and the collapse times can be even smaller. So what happens is that those regions can become a star, while the whole whatever you call whole nebulae may be feeling some self-gravity. The time scale over which it can collapse will be much larger compared to the time scale over which shorter regions can collapse. Now the question is, if I introduce some perturbation, why should the perturbation should have a one characteristic scale in the problem? So the perturbation can occur over a small scale or a large scale, right?
Yes.
Which may mean that in a cloud you will have a range of scales over which perturbation will occur, because of which the range of masses will go through this Jeans instability. But Jeans instability may be local. The whole nebulae may be Jeans stable, but inside it may be Jeans unstable. I think this you have to understand, otherwise this is the problem will come back to you again when you study galaxies and other things. So this is like a big region. A small region can go through perturbations, and this region need not have the same mass, radius and all. Okay, so that can lead to mass functions. Mass functions means number of clouds with different masses will be formed, and they will go through and form stars. That's why I wanted to introduce this whatever I call initial mass function. I will do it in the afternoon.
Thank you, sir.
Okay, we'll take one question from Yashodhan Joshi. I've unmuted you. I've now unmuted you. Yeah.
Sir, I wanted to ask that you said most of the time stars continue up to the iron stage, and usually they don't fuse like iron after that. So how the heavy elements like uranium, etc., are formed?
Yeah. Because why you cannot fuse hydrogen, right? Sorry, why you cannot fuse iron, because iron is the most stable element.
Yes, sir.
So you cannot keep forming any element heavier than iron in an equilibrium condition. Because you form iron, it will break into a smaller atom. So you don't form element heavier than iron in an equilibrium condition. You understand what you mean by equilibrium condition? You can't keep the same temperature. You form it at a temperature, and if the temperature is high, this iron will break into smaller things. So you have to form. So the trick is interesting, right? You need high temperature, high density, and heavier element. They fuse to form iron. Then what you have to do? You have to make sure that iron doesn't destroy, or iron doesn't due to iron fission doesn't occur. So how to stop it? You form, and immediately you make sure that the region is lower temperature, lower density, so it doesn't destroy, or the fission doesn't occur. Okay, so this is what happens. So you form them in what is known as supernovae. When the star dies, the star has a lot of heavier elements. The heavier elements will travel with high speed outside because expanding. Dipankar showed you nice pictures of supernova remnants, right? This supernova, when they go, they have high speed, higher temperature, so they can fuse. Things can fuse and form elements. But since they are expanding and the density is continuously falling and the temperature is continuously falling, the newly formed heavier elements can survive like heavier elements. Okay. So this is the process one uses to form them, not in equilibrium, long-term equilibrium like in main sequence. I hope I answered your question.
Okay, so we are almost at 11:15. I'll take one last question. Unix Sengupta has a second question, and then we will stop for today. So So, Unique, I've unmuted you.
So the second question which I got is actually related to the HR diagram. So in the HR diagram, we have fitted the main sequence stars, we have fitted white dwarfs, giants, and supergiants. So is there a possible way we can fit neutron stars and black holes into the HR diagram also?
I'm sorry, because you have to detect, this is the absolute magnitude, right? This is done in optical colors, and neutron stars are usually pretty weak in optical, because you detect neutron star in this thing, and black hole. I would think that black hole. See, this is basically optical diagram, right? Based on optical. I mean, just it's okay. You can keep them in some sequence of events. Yes, I mean they will be somewhere here, right? I mean, if you are thinking of because neutron star, you don't see, you can detect them. People try to detect optical light from neutron star, but that is not because of two reasons. You can guess, right? Their surface area is so small. You know the size of neutron star, I suppose.
Yeah, of course. It's very small.
Yeah, so that's all. So optically, and black hole has no physics related to this, so you cannot light coming from black hole is nothing to do with any process we discussed.
Yes, of course. There is no optical observation from black holes. Thank you, sir.
Okay, so Anand, maybe we can either stop, or if you want, you can just glance at the YouTube questions. Sykes is saying that he has tried to address most of the questions while the talk was going on.
Okay, so what I can do is that I can have a look at this in the afternoon. If needed, I start the questions. I start my lecture answering those questions. Because we have around 15 minutes.
Yeah. Maybe if you join a few minutes early, you can just take a look at the question, or you can take a look on your own.
Yeah, I'll do that.
Okay, so let's stop here. Sorry that we can't address all questions.